So I want you to look at your hand right now, like really look at it.
Right, just take a second to actually look.
Yeah, and think about the iron pulsing through the blood in your veins right now. Think about, the calcium giving structure to your bones.
The oxygen you're breathing.
Exactly, the oxygen you're pulling into your lungs at this exact second, and the carbon that forms the structural backbone of basically absolutely every single organic molecule in your body.
It's all there.
It is. But here's the crazy part. None of that material existed when the universe began. Literally not one atom of it.
Yeah, it's a completely sobering thought because, if we rewind the clock 14 billion years to the dawn of the universe, right after the Big Bang, the cosmos was essentially just a massive, expanding cloud of the absolute simplest, lightest elements possible.
Just the absolute basics.
Right. You had an ocean of hydrogen, you had a little bit of helium, a microscopic dusting of lithium, maybe, and that was really it. The universe was completely sterile, chemically speaking.
There was just nothing there to work with.
Exactly. There was simply no heavy, complex material available to build a rock, let alone a planet or an ocean or, a human being.
So to get from a vast, boring cloud of plain hydrogen gas to a universe that has a rocky Earth and coffee and skyscrapers, and you listening to this right now, something had to build those heavier elements from scratch.
Something had to manufacture them.
Right. And today on this deep dive, we are figuring out exactly how the universe built you. We are going to trace the epic, multi-billion-year life cycle of a star.
From a freezing, dark cloud of gas all the way to its spectacular apocalyptic death.
Because a star isn't just a pretty light twinkling in the night sky. It's really a colossal cosmic manufacturing plant. It takes in raw, basic hydrogen, subjects it to conditions that break the laws of normal physics, and turns out the ingredients for life.
That's the perfect way to look at it.
But I want to start at the very foundation here. Okay, let's unpack this. Before we can talk about a star manufacturing anything, how do you actually build an element from scratch? Or rather, how do we even define what a star is to begin with?
Well, at its most fundamental level, a star is a giant ball of gas. Overwhelmingly that primordial hydrogen and helium we just mentioned. And it's held together entirely by its own immense gravity.
Okay, gravity.
Right. Held together by gravity with a core that is hot and dense enough to run a continuous nuclear fusion reactor.
I actually have to pause you on that first part because held together by its own gravity, when we think of gravity, we intuitively think of a planet pulling us down, right?
Sure, like dropping an apple.
Exactly. You drop an apple, it falls to the Earth. The idea that a cloud of gas, something we usually associate with being weightless, like a wisp of smoke, has enough collective mass to exert an intense gravitational field, that's hard to visualize.
It is a common hurdle, definitely, because human intuition is built for a tiny planetary environment. But mass is mass.
Right.
Every single particle of matter in the universe exerts a gravitational pull on every other particle. So a single atom of hydrogen has a gravitational pull. It's infinitesimally small, but it's non-zero.
It's there.
It's there. Now, if you gather unimaginably huge quantities of those atoms, we're talking trillions upon trillions upon trillions of miles of gas, all those microscopic gravitational pulls add up to an overwhelming force.
Like compound.
Exactly. Gravity is relentless. It is constantly pulling every single atom of that gas inward, basically trying to crush the entire cloud down into a single microscopic point at the center.
Okay, so if gravity is pulling everything inward with that much ferocity, why doesn't the star just instantly collapse into a dot? Like, why is it a sphere at all?
Because there is a counterforce fighting back.
Okay.
And that counterforce is radiation pressure. Deep in the core of the star, that nuclear fusion reactor is running, and it's generating incomprehensible amounts of outward-pushing energy and heat.
So it's pushing back out.
Right. That outward pressure pushes against the crushing weight of the gas. So a star's entire existence is defined by this single foundational conflict. Gravity pulling matter inward versus thermal and radiation pressure pushing matter outward.
A constant tug of war.
Exactly. Astronomers call this state hydrostatic equilibrium.
Hydrostatic equilibrium. I always picture it kind of like inflating a balloon.
Oh, that's a good analogy.
Right. The rubber of the balloon is gravity. It is constantly stretched, constantly trying to contract and crush the air inside. But the air pressure inside the balloon is pushing back outward against the rubber.
Yes.
And as long as the inward squeeze of the rubber and the outward push of the internal air pressure are perfectly matched, perfectly equal, you have a stable, round balloon.
Which is the star.
Right. If the rubber gets weak or you pump too much air in, the outward force wins and it pops. If you let the air out, the rubber wins and it collapses.
The balloon analogy captures the mechanics perfectly, honestly. And when you apply that mechanic to the scale of a star, it fundamentally changes how you look at the night sky.
How so?
Well, a star is not a peaceful, static, glowing orb. It is an incredibly violent, continuous explosion that is being constantly contained by its own weight. The tension is almost unimaginable. It is basically a bomb that takes billions of years to finally go off. The moment that outward pressure falters even a little bit, gravity is waiting to instantly crush it.
That is genuinely terrifying, but it makes so much sense. It's a perpetual tug of war.
Yeah.
So how does this violent balancing act actually begin? You'd think a cosmic furnace starts in some incredibly energetic, chaotic environment, right?
You would think so, yeah. But the reality is that the birthplace of a star is one of the coldest, emptiest seeming places in the entire galaxy.
Really? Where is that?
The cosmic womb is what astrophysicists call a giant molecular cloud.
Okay.
These are vast, freezing, extremely tenuous nebulas of gas and dust just drifting through the spiral arms of our galaxy. And when we say vast, I mean we are talking about structures that can span hundreds of light years across.
Hundreds of light years.
Yeah. Light, traveling at 186,000 miles per second, takes centuries just to cross from one edge of this cloud to the other.
And it's mostly just sitting there, freezing cold. But space isn't perfectly smooth, right? Inside this massive cloud spanning hundreds of light years, the gas isn't distributed with perfect mathematical evenness.
Exactly right. These clouds have structure. They have internal currents, eddies, and clumps. In a cloud that unimaginably huge, eventually you will find a localized region where the density of the hydrogen gas happens to be just a tiny fraction higher than the gas surrounding it.
Just purely by chance.
Purely by chance. And that incredibly slight increase in density gives gravity the tiny advantage it needs to take over.
Because more mass in one spot equals a slightly stronger gravitational pull in that exact spot.
Yes. That slightly denser clump begins to gently pull in the individual atoms of gas from its immediate surroundings. As it pulls in more gas, the clump gains more mass.
And more mass means more gravity.
Exactly. Because it has more mass, its gravitational pull gets even stronger, which means it can reach out further and pull in even more material even faster. It becomes a runaway snowball effect, a completely localized collapse within this giant freezing cloud.
But this runaway snowball process, that takes millions of years on its own. Sometimes it gets a violent shove to speed things up, doesn't it? What kind of trigger can jumpstart a star?
Space might look like a silent vacuum, but it's actually a deeply dynamic environment. A very common trigger for star formation is a shock wave from a nearby supernova, a dying, exploding star.
Wait, how does a shock wave travel through space? On Earth, a shock wave from an explosion travels through the air. It compresses the atmosphere. But space is a vacuum. What is actually waving?
It's a great question because we do think of space as completely empty, but inside a molecular cloud, it isn't a true vacuum. There is a very, very thin soup of gas and dust.
Oh.
So when a star explodes nearby, it sends a massive wave of kinetic energy ripping through that thin soup. When that shock wave slams into our cold molecular cloud, it physically rams the gas particles together, instantly compressing them.
Just squishes them all into one spot.
Right. It forces them to clump up, handing gravity a massive, sudden head start. Another trigger can be a kind of galactic traffic jam. That happens when a cloud slowly orbits into the denser spiral arm of a galaxy, and it just squishes the gas together.
Okay, so the gas is clumped, whether by a shock wave or just slowly over time, and it starts collapsing inward in this runaway snowball process. And as this millions of miles wide clump of gas collapses, it heats up.
It does.
Let's break down the mechanics of this heating, because no one is out there lighting a cosmic match in the nebula. Why does a cloud of gas falling inward suddenly get hot?
We can trace this directly to a physics concept, the conversion of gravitational potential energy into kinetic energy.
Okay, potential to kinetic.
Yeah. Think of dropping a heavy bowling ball off the edge of a tall building. Before you drop it, while it's just being held there, it possesses potential energy due to gravity.
Yeah.
The moment you let go, it falls and speeds up.
Right.
That potential energy is being actively converted into kinetic energy, which is the energy of motion.
So all these countless trillions of hydrogen atoms
Right.
are essentially falling toward the center of the cloud due to gravity, and they are speeding up as they fall.
Precisely. And as they all rush down a gravitational funnel toward the center, getting squeezed into a tighter and tighter physical space, they start colliding.
Bumping into each other.
Violently. At a microscopic level, temperature is just a measurement of how fast particles are moving and how violently they are smashing into one another.
Right. Heat is just movement.
Exactly. High kinetic energy means fast-moving particles. Fast-moving particles mean high heat. So as the cloud physically shrinks under its own weight, the hydrogen atoms move faster, they smash together more violently, and the overall temperature of the gas begins to skyrocket.
And it doesn't just heat up either. It also starts to spin, right? There's a specific physics term here, conservation of angular momentum, which sounds incredibly dense, but it's something we see in sports all the time.
It really is.
Think of an Olympic figure skater.
The figure skater analogy is the absolute classic, most accurate way to visualize this physical law.
Right. Because when a skater's doing a spin on the ice and they want to spin faster, they don't push off the ice again. They start with their arms spread wide, spinning somewhat slowly. But the moment they pull their arms in tight across their chest, their rotation dramatically, instantly speeds up.
They become a blur.
Exactly, a blur. That is the conservation of angular momentum. The mass of the skater's arms is moving closer to the center axis of their rotation, so the speed of the rotation has to mathematically increase to conserve the total energy of the system.
And the exact same mathematical law applies to this collapsing cloud of gas.
Because it's pulling its arms in.
Right. Before the collapse, the cloud had a tiny, almost imperceptible drift or rotation to it. As millions of miles of that gas get pulled inward, closer and closer to the center axis, the entire cloud starts spinning faster and faster.
Just like the skater.
Exactly. And as it spins furiously, the centrifugal force causes the cloud to flatten out along its equator. Imagine taking a ball of pizza dough and tossing it spinning into the air.
It flattens out.
Right. The spinning force flattens the ball into a wide disk.
So we go from a giant, shapeless blob of freezing gas to a rapidly spinning, flattened disk with a huge, dense, furiously hot concentration of gas gathering right in the very center.
That central, glowing concentration of gas is a protostar. It's the seed of the new star.
And what I absolutely love about this is how it connects directly to our everyday lives here on Earth right now.
Oh, absolutely.
Because that spinning, flattened disk of leftover gas surrounding the protostar, that is a protoplanetary disk. That is the exact material that will eventually clump together over millions of years to form asteroids, moons, and planets.
The building blocks of our neighborhood.
Which completely explains why our solar system is shaped the way it is today. It's the reason why our planetary system is relatively flat, and why all the planets from Mercury all the way out to Neptune orbit the Sun in the exact same direction. We are all just riding the leftover angular momentum of that original collapsing, spinning cloud from 4.5 billion years ago.
It's essentially cosmic archaeology. You can look at the flat orbital plane of the planets in our solar system right now, tonight, and perfectly deduce the physical mechanics of the giant molecular cloud that birthed our sun. The motion is perfectly preserved.
It's incredible.
Oh.
Okay, so we have this glowing protostar in the center of the disk. It's pulling in more material, getting denser, spinning faster, and getting incredibly hot as all these particles violently collide. But it isn't a true star yet, is it?
No, not yet.
It's just a really hot, dense ball of gas.
Yes.
It needs to reach a very specific magical temperature threshold.
Right. For hundreds of thousands of years, gravity is winning the tug of war. It is crushing the protostar tighter and tighter, driving the temperature higher and higher. Finally, the core reaches a critical threshold, roughly 10 million degrees Celsius.
10 million degrees. Wait, let me play devil's advocate here for a second. How do we actually know the core is 10 million degrees? We can't exactly stick a giant thermometer into a star.
Well, we know through the rigorous application of thermodynamic gas laws and mathematics.
Okay, math to the rescue.
Always. We can measure a star's mass by observing its gravitational effects, and we can measure its physical size. Once you know the total mass pressing inward and the volume it occupies, physics dictates exactly how much thermal pressure is required pushing outward to prevent it from collapsing.
You balance the equation.
Right. When you crunch those numbers for a stable star, the mathematical reality requires a core temperature of at least 10 million degrees to generate the necessary pressure. And 10 million degrees is the magical ignition point for nuclear fusion.
This is where the magic trick of the universe happens. Let's be very precise here, because fusion is a word that gets thrown around in sci-fi a lot. What is literally happening to the atoms at 10 million degrees?
To understand the mechanics of fusion, we have to look at the anatomy of a hydrogen atom. Hydrogen is the simplest element in the universe. Its nucleus consists of just one single proton.
One proton, got it.
And protons have a positive electrical charge. And as anyone who has ever played with magnets knows, charges repel each other. If you try to push the two positive ends of a magnet together, you feel this invisible force field pushing back.
The closer you get, the harder it pushes back.
Exactly. In physics, this is called the Coulomb barrier, or electromagnetic repulsion. Under normal conditions, if two hydrogen protons are drifting toward each other, this electromagnetic repulsion acts like a bumper. It pushes them away from each other. They veer off or bounce away long before they ever physically touch.
But inside the core of this protostar, conditions are the furthest thing from normal. The temperature is 10 million degrees, and the physical pressure from all the mass of the star crushing down on the core is just incomprehensible.
Yeah, the rules change here. Because the temperature is so high, the protons aren't just drifting, they are moving at blinding, frantic speeds. And because the pressure is so immense, they are packed shoulder to shoulder in an impossibly tight space.
No room to move.
Right. They are moving so fast and are so densely packed that they can actually overpower that natural electromagnetic repulsion. They literally smash head-on into each other with so much kinetic energy that they breach the barrier.
They break through the force field.
Yes. They get so microscopically close that a different, much more powerful fundamental force takes over. And that is the strong nuclear force.
The strong nuclear force. I've heard this described as the superglue of the universe.
Superglue is the perfect analogy, honestly. The strong nuclear force is vastly stronger than electromagnetic repulsion, but its range is ridiculously short. It only operates at subatomic distances.
Okay, so it has to be really close.
Right. It's like having a piece of Velcro on those repelling magnets. The magnets violently want to push apart, but if you slam them together hard enough that the Velcro touches, the Velcro engages and holds them permanently together.
I love that.
Yeah, you have to force the protons to essentially touch before the strong nuclear force activates. But once they do, it snaps them together. Through a rapid chain of subatomic steps known as the proton-proton chain, 4 individual hydrogen nuclei, 4 single protons, are smashed and glued together to become one single helium nucleus.
4 hydrogens become 1 helium. The factory has finally produced its first new product. But why does this matter for the survival of the star? Why does building a helium atom stop the star from collapsing under gravity?
Because of a quirk in the math of the universe, which gives us one of the most mind-bending physical realities in all of science.
Okay, lay it on me.
If you take the mass of the 4 individual hydrogen protons that went into the collision and you put them on a microscopic scale,
Right.
and then you take the mass of the one brand new helium nucleus that comes out of the collision and put it on the scale, the weights do not match.
Wait, how is that possible? If I take 4 blocks of clay and smash them into 1 block of clay, it weighs the exact same amount.
In our everyday macroscopic world, yes. But in nuclear physics, the resulting helium nucleus is roughly 0.7% lighter than the 4 hydrogens that formed it.
So 0.7% of the actual physical matter has just vanished from existence.
Yeah.
Where did the mass go?
It didn't vanish. It transformed. That missing mass turns entirely, 100%, into pure energy. And to understand exactly how much energy we are talking about, we look to Albert Einstein's famous equation, E equals mc squared.
Right. Everyone knows EMC starting from pop culture.
Yeah.
But visualizing what it actually dictates is tough. Let's break it down for everyone.
Basically, the equation is a conversion rate. It tells us how much energy is locked inside a piece of solid matter. The m is the mass you're converting. The c is the speed of light.
Which is huge.
Which is an absolutely huge number, roughly 300 million meters per second.
Yeah.
But the equation doesn't just multiply the mass by the speed of light, it multiplies it by the speed of light squared.
Right.
You take 300 million and multiply it by 300 million. You get an utterly staggering, monumental multiplier.
To put that in perspective, if you could perfectly convert a single paperclip into pure energy using EMC-THAC, it wouldn't just give you a little spark, it would release the energy of an atomic bomb.
Exactly, a paperclip. So when those 4 hydrogen protons fuse into helium, and that tiny 0.7% of their mass is converted into energy via EMC-THAC, it creates a microscopic yet incredibly violent explosion of pure energy and light.
And that's just one atom.
Right. Now multiply that single subatomic reaction by the countless trillions of hydrogen atoms fusing in the core every single fraction of a second. This continuous titanic release of fusion energy is what generates the intense outward radiation pressure.
The outward push.
Yeah.
That's the air in the balloon.
Yes. The outward force of this fusion energy is finally, suddenly strong enough to push back against the crushing inward weight of gravity. The collapse halts. The star stabilizes. The engine is officially on.
I just want to pause and marvel at the sheer scale of this machinery. Because just looking at our own sun, an average, everyday star, the numbers are hard to process. The sun converts roughly 600 million tons of hydrogen into helium every single second.
Every single second. Tick, 600 million tons. Tick, 600 million tons.
And because of that 0.7% mass deficit in the fusion process, the sun is physically losing about 4 million tons of physical mass, converting it into pure energy every single second. 4 million tons.
It's wild.
Imagine taking a dozen massive ocean cargo ships, dropping them into a magical wood chipper that instantly vaporizes them into light and heat, and doing that every single second of every single day. And here's where I have to push back on this scale because my brain basically projects it.
Go for it.
The sun loses 4 million tons of matter a second, and it's been doing this nonstop for 4.6 billion years. How is there any sun left?
It's the perfect question, and it beautifully highlights how terrible human brains are at comprehending the true size of celestial bodies.
We just can't scale it up.
No, we really can't. A loss of 4 million tons a second sounds apocalyptic, but the total mass of the sun is so incomprehensibly vast that losing 4 million tons a second for 4.6 billion years means the sun has still only consumed a tiny fraction of a percent of its total mass.
Seriously.
A fraction of a percent.
Yes, it is a rounding error in the grand accounting of the star. Over 1 million Earths could fit inside the volume of the sun. The fuel reserves are staggering.
That just breaks the brain. It really does.
It does. But because it possesses such deep reserves of fuel, this ignition point allows the star to enter a very long, incredibly stable phase of its life. Astronomers refer to this phase as the main sequence.
The main sequence. This is the sweet spot. This is the era of stability.
It is the era of equilibrium. The main sequence is simply the period where that foundational tug-of-war we talked about is perfectly balanced. Gravity pushing in, nuclear fusion pushing out.
Right. A star will spend about 90% of its entire lifespan in this peaceful main sequence phase. Our sun is a main sequence star right now, roughly halfway through its allotted time in this phase.
Stable, reliable, pouring out sunlight, and keeping our planet warm without blowing us up.
Yeah.
We appreciate the main sequence. But the light keeping us warm takes an incredibly long time to actually reach us, right? I've read about this concept called the random walk.
Yes, the random walk of a photon. It's fascinating. When that fusion reaction happens in the core and releases a particle of light, a photon, that photon doesn't just shoot straight out into space.
It doesn't just fly away.
No. The core of the star is so dense, so packed with chaotic, fast-moving particles, that the photon instantly crashes into another particle, bounces off, crashes into another, bounces again in a highly chaotic zigzag pattern.
Like a pinball machine.
Exactly like a pinball machine.
Yeah.
And it takes that photon on average about 100,000 years of bouncing around inside the star just to reach the surface. And once it hits the surface, it takes 8 minutes to cross the vacuum of space to hit your eye on Earth. So the sunlight warming your face right now was actually manufactured in the core of the sun before human beings even existed.
That is profound. Okay, so once a star is happily burning away on the main sequence, zigzagging photons and all, what dictates its future? I know stars come in different colors and sizes. What trait determines how a star will live and die?
Well, once a star settles onto the main sequence, its ultimate destiny, its core temperature, its surface color, its overall brightness, exactly how long it will live, and the precise, violent manner in which it will die. All of that is already sealed by one single overriding characteristic.
Just one.
Just one. Its mass. Simply put, how much gas did it manage to pull together during that initial collapse before fusion ignited?
Mass determines everything. But the relationship between a star's mass and its lifespan is deeply counterintuitive.
Yeah.
You would naturally assume that a star with way more mass, meaning way more fuel, would live a lot longer. More fuel in the tank means a longer road trip, right?
You would assume that, but the physics dictate the exact opposite. More massive stars have exponentially more fuel, but they live dramatically shorter lives.
Why? If you have more fuel, why do you die faster? That doesn't make sense.
Because higher mass means a much, much stronger gravitational pull. Higher gravity means the core is being crushed with unimaginably greater pressure. To avoid collapsing under that crushing weight, the core has to fight back with equally immense outward thermal pressure.
Oh, I see.
Right, and the only way to generate that massive outward pressure is to run the nuclear fusion engine much, much hotter and faster. So a massive star is forced to gorge on its vast reserves of fuel disproportionately fast just to maintain equilibrium.
Right. Here's where it gets really interesting to me. I like to compare this to vehicles.
Okay, let's hear it.
Think of a massive, super heavy blue giant star as a giant monster truck. Yes, it has a fuel tank the size of a swimming pool. It has tons of fuel. But because the vehicle is so massive and heavy, the engine has to work ridiculously hard just to keep it moving forward.
It's a gas guzzler.
Exactly. It guzzles gas.
Yeah.
It burns through that swimming pool of fuel in no time at all. But a tiny, low-mass star, a red dwarf, is like a highly efficient little compact hybrid car.
Perfect analogy.
Right. It has a tiny gas tank, but the car is so light that the engine barely has to work. It sips fuel so slowly, so efficiently, that it can drive almost forever on a single tank.
The vehicle analogy maps perfectly. Let's look at the extremes to see how wildly different these lifespans can be. Take that compact car, the red dwarf. These are stars with perhaps only 10 or 20% of the mass of our sun. Our nearest stellar neighbor, Proxima Centauri, is a red dwarf.
Very small.
Very small. Because their mass is so low, their gravity is relatively weak, the core isn't being crushed very hard, so they don't need a massive outward push to survive. They fuse their hydrogen incredibly slowly at a very low temperature. Because they are cooler, they emit a dim, reddish light.
And because they sip their fuel so slowly, what kind of lifespan are we talking about here?
We're talking lifespans on the order of hundreds of billions up to 1 trillion years.
1 trillion years? But wait, the universe itself is only about 13.8 billion years old?
Exactly. Which leads to one of the most fascinating facts in all of astrophysics.
Like that?
No red dwarf has ever died of old age in the entire history of the universe.
Never.
Never. Every single red dwarf that has ever been born since the dawn of time is still out there, slowly, quietly burning away. They outlive everything else by orders of magnitude. Furthermore, red dwarfs are fully convective, meaning the material inside them constantly churns and mixes like a boiling pot of water.
Stirring it up.
Right. It brings fresh hydrogen from the outer layers down into the core, ensuring every last drop of fuel gets used.
Wow. Okay, so that's the compact car. What about a mid-sized sedan, like our sun?
A sun-like star has moderate mass, meaning moderate gravity. It burns hotter and brighter, usually a yellow-white color, and goes through its fuel at a moderate pace. Its main sequence lifespan is roughly 10 billion years.
10 billion years. And then we have the monster trucks, the heavyweights.
The massive blue giants. Take a star like Rigel in the constellation Orion. These can be 20, 40, even 80 times the mass of the sun. Their core gravity is so astronomically crushing that they have to burn furiously at staggering temperatures just to stave off instant collapse.
They're blazing hot.
They blaze hot, incredibly bright, and blue in color. But because they're burning at such a frantic rate, they exhaust their massive fuel supplies in only a few million years. In cosmic terms, it's a flash in the pan.
Live fast, die young.
Exactly. Live fast and die very young. Bigger always means brighter, hotter, bluer, and significantly shorter-lived.
Okay, so let's walk down the timeline. Eventually, whether it takes 3 million years for a blue giant or 10 billion years for a star like our sun, the fuel tank runs empty. The hydrogen in the core has all been fused into helium. There is no more hydrogen left to burn in the center.
And that exact moment is when the foundational balance, the equilibrium, breaks.
Oh boy.
Yeah. The outward radiation pressure from hydrogen fusion drops to near zero, and gravity immediately, violently takes over.
The air is let out of the balloon, and the rubber just crushes inward.
Yes. Gravity wins. What happens next is a complex cascade of events that depends entirely on the star's mass. Let's trace the death of a mid-sized star, a sun-like star, to see the definitive future of our own solar neighborhood.
Okay, let's trace this out step by step. Core hydrogen runs out. Fusion stops. Radiation pressure drops. Gravity takes over. The core gets crushed.
Whoa.
What does that physical crushing do to the inside of the star?
Remember the physics of the collapsing gas cloud from the star's birth.
Potential to kinetic energy. It heats up.
Right. The same thermodynamic principles apply here. The dead helium core is suddenly contracting rapidly under the crushing weight of the star. As it compresses, it converts potential energy into kinetic energy. It heats up. The core actually gets much, much hotter than it ever was during the main sequence.
Okay.
Now, while the core itself is out of hydrogen, there is a shell of gas immediately surrounding the core that still has unburned hydrogen in it.
Like a wrapper.
Right. The collapsing core gets so blisteringly hot that it actually ignites fusion in that shell of hydrogen around the crushed core.
So the center is dead helium, but a ring of fire ignites right outside of it.
Exactly. We call this shell burning. And this shell burns fiercely. The energy released by this new hydrogen shell burning is immense. It pushes outward against the upper layers of the star with much greater force than the core ever did.
Wow.
This intense new outward pressure causes the outer layers of the star to swell up enormously. The star balloons in size. And as these outer gaseous layers expand millions of miles away from the hot core, they naturally cool down. And in physics, as a glowing object cools, its emitted light shifts toward the red end of the spectrum. The star has officially become a red giant.
A red giant. So bringing this cosmic scale down to our local reality, what does this mean for us? What actually happens to Earth when our sun runs out of core fuel and balloons into a red giant?
Well, astrophysicists have mapped out a pretty precise timeline for this. In roughly 5 billion years, our sun will undergo this exact transformation. Its outer layers will expand tremendously. It will physically swallow the orbit of Mercury. It will swallow the orbit of Venus.
Oh, wow.
And it is highly likely that the expanding surface of the sun will reach all the way out to Earth's current orbit.
It will literally, physically swallow the Earth. The planet will be inside the star. That sounds like a definitive end to humanity. But I should offer a grim sort of comfort here to you listening based on the timelines. Earth won't be around to be swallowed anyway, right?
Right. Yeah, long before the red giant phase, life on Earth will be over.
Great.
Even while stable on the main sequence, as helium slowly builds up in the sun's core, the core becomes slightly denser, which makes it burn just a little bit hotter to maintain equilibrium.
Oh, so it's getting hotter now.
Yes. Because of this, the sun's luminosity is gradually increasing. Over the next billion years, that gradual brightening, about a 10% increase in heat, will be enough to completely boil away Earth's oceans, trigger a runaway greenhouse effect, and strip our atmosphere.
Yikes.
So in 1 billion years, Earth is a scorched, sterile rock. In 5 billion years, it gets swallowed by the red giant.
Good to know we have exactly 1 billion years to figure out interstellar travel. But let's go back inside the dying red giant. The outer layers have swelled up and swallowed the inner solar system. But what is happening down in the dead helium core? It's still being crushed by gravity.
Yes, gravity never stops. The core keeps compressing and getting hotter and hotter. Eventually, it hits a new extreme temperature threshold, roughly 100 million degrees.
100 million.
Yes, this is vastly hotter than the 10 million degrees needed for hydrogen. At 100 million degrees, the core gets hot enough to force those heavy helium nuclei to overcome their even stronger electromagnetic repulsion. The core abruptly ignites again, this time fusing helium into heavier elements, specifically carbon and oxygen.
Okay, so the manufacturing plant is upgrading its machinery. We made helium. Now we're taking that helium and smashing it together to make carbon and oxygen, the literal building blocks of organic life.
Indeed. It's a process called the triple alpha process, where 3 helium nuclei fuse to form 1 carbon nucleus. But for a mid-sized star like our sun, this is where the manufacturing process permanently stops.
Why? Why can't it just keep going? It have carbon now. Why not crush the carbon and fuse it into the next element?
Because a sun-like star simply doesn't have enough mass.
It's not heavy enough.
Right. Once the helium fuel runs out, leaving a core mostly made of carbon and oxygen, gravity tries to crush it again to heat it up to the next ignition threshold. But a mid-sized star just doesn't have enough overall mass, enough gravitational weight, to ever compress the core hard enough to reach the hundreds of millions of degrees needed to force carbon nuclei to fuse.
So it just stalls out.
The furnace goes cold. It has reached its physical limit.
So when the helium runs out, fusion ceases permanently. Gravity has squeezed as hard as it possibly can, but it's just not strong enough to light the next fire. What happens to the star then?
It undergoes a rather quiet, surprisingly beautiful death. Without the intense radiation pressure of core fusion to hold everything up, the star becomes unstable. The outer layers of the red giant, which are already incredibly swollen, very cool, and only loosely bound by the star's gravity at that vast distance, they begin to pulse.
Just kind of wobbling.
Yeah, and eventually they just sort of puff off. They gently detach and drift away into deep space over thousands of years, forming a vast, expanding shell of glowing gas.
Astronomers call this expanding glowing shell of drifted gas a planetary nebula, which, let's be clear, is a terrible, highly confusing name.
It is a completely misleading name. It has absolutely nothing to do with planets.
Nothing at all.
None. It's a historical artifact from the late 1700s. When early astronomers, like William Herschel, looked at these expanding shells of glowing gas through primitive telescopes, they looked round, distinct, and somewhat fuzzy, bearing a strong visual resemblance to the newly discovered planets Uranus or Neptune.
Oh, wow.
So Herschel called them planetary nebulae, and the name stuck, confusing astronomy students ever since.
So the outer layers drift away to form a beautiful, glowing nebula. But what is left behind in the center, the core is still there, right?
What remains in the absolute center is the naked, exposed, dead core of the star. We call this remnant a white dwarf. It is composed entirely of that manufactured carbon and oxygen. It is roughly the physical size of the Earth, but it contains a substantial fraction of the mass of the entire original sun.
Taking the mass of a star and crushing it down into a sphere the size of a planet, the density of that material is hard to wrap my head around.
The density is staggering. A great way to visualize it. A single teaspoon of material scooped from a white dwarf would weigh several tons here on Earth.
Tons, a teaspoon.
Yes. The material is crushed so tightly that normal atomic structure breaks down. The atoms are packed so closely that the electrons are stripped from their nuclei, swimming in a dense quantum soup. The only thing stopping a white dwarf from collapsing further under its own immense gravity is a quantum mechanical rule called electron degeneracy pressure.
Let's break that rule down, because electron degeneracy pressure sounds like something out of Star Trek.
It stems from the Pauli exclusion principle in quantum mechanics, which states that no two electrons can occupy the exact same quantum state in the same physical space at the same time.
Okay.
Imagine trying to cram people into a small elevator. At first, they just bump shoulders, but eventually the elevator is entirely full. People physically push back against anyone trying to shove another person in. They can't fit. Right. The electrons in a white dwarf are the people in the elevator. Gravity is trying to crush them into a smaller space, but the laws of quantum mechanics say, no, the elevator is full. The physical resistance of those electrons pushing back is what holds the white dwarf up.
But the white dwarf is entirely dead, right? It isn't fusing anything.
Right. It is essentially a cosmic ember. It simply radiates its immense leftover heat from its former life as a star, slowly cooling down over tens of billions of years. Eventually, when it loses all its heat, it will become a black dwarf, a cold, dark, dead lump of carbon floating unseen in the void.
That is the ultimate fate of our sun. A long, stable life, a swelling red expansion, a gentle puffing away of its outer layers, and then an eternity as a glowing, cooling ember. But what if a star has enough mass to keep fighting gravity? What if we look at the heavyweights, the blue giants? Because the story of their death gets much faster and much, much more violent.
This is where stellar physics gets truly spectacular. We are talking about massive stars, stars above roughly 8 times the mass of our sun. When these giants run out of helium in their core and the core collapses, their story doesn't end. They actually do have enough gravitational weight to crush the core hot enough to fuse carbon.
Because they have so much mass pressing down, the pressure and heat generated by the collapse is vastly greater, so carbon catches fire.
Yes, they fuse carbon into neon. And when the carbon runs out, the core collapses again, heats up even more, and fuses neon into oxygen. Then oxygen into silicon. With every new element, gravity tries to crush the star to death, and the star staves off collapse by unlocking a new, hotter, harder-to-reach fuel source.
This sounds like a desperate battle. The star's just scrambling, trying to find something, anything, to throw into the furnace to push back against gravity.
It is a desperate, losing battle. And what's crucial to understand is the accelerating timeline of this process. Each successive stage of fusion requires profoundly higher temperatures to ignite.
Right.
And crucially, each heavier element yields less and less outward energy per reaction, meaning the star has to burn through the new fuel exponentially faster just to maintain the same outward pressure against gravity. Furthermore, at these extreme temperatures, the star starts losing massive amounts of energy through the emission of neutrinos, which ghost right out of the core, robbing it of heat.
So it's not like it spends a billion years burning carbon and a billion burning neon. The clock is speeding up.
Accelerating terrifyingly. For a massive heavyweight star, hydrogen burning took a few million years. Helium burning might take a few 100,000 years. Carbon burning lasts maybe a few centuries.
Wow, just centuries.
Yeah. Neon burning lasts a few years. Oxygen burning takes about 6 months. Silicon burning, the absolute final stage, lasts only a matter of days.
Wait, days. A star that has lived for millions of years burns through an entire core of silicon in days.
Yes. The core is at unimaginable temperatures, billions of degrees, frantically fusing silicon just to maintain the outward pressure against a truly monstrous gravitational force. And inside the star, an incredibly complex structure has formed. Because of the different temperature zones required for each element, you get an onion-like layered structure.
Let's picture this onion structure. What does the inside of this dying heavyweight look like right before the end?
Imagine taking a sword and slicing the star in half. At the very outer edge, you have a vast envelope of unburned hydrogen. Moving inward, where it's hotter, you have a shell fusing hydrogen into helium. Inside that, a hotter shell fusing helium into carbon. Inside that, carbon fusing to neon, then a shell of neon to oxygen, then oxygen to silicon.
Shells within shells.
Exactly.
Yeah.
You have these concentric layers, these burning shells, with heavier and heavier elements settling toward the center. It's an onion made of nuclear fire, all burning simultaneously, desperately fighting the crush of gravity.
That is an amazing image, building heavier and heavier elements as you go deeper into the furnace. But this incredible chain of fusion has a hard mathematical limit, a crucial bottleneck. The process ends abruptly at iron. Why iron? Why can't it just squeeze the iron hard enough to fuse it into gold or lead or something else?
Because of a fundamental law of nuclear physics known as the nuclear binding energy curve. Remember how fusing hydrogen into helium resulted in a tiny loss of mass, which was released as energy via E as in Seaway?
Yes, the explosion of energy that pushes outward and keeps the star alive.
Right. Fusing all those lighter elements, hydrogen, helium, carbon, oxygen, all the way up to silicon releases energy. It pays out. It's an exothermic reaction. It gives the star the outward radiation pressure it needs to fight gravity. But iron sits exactly at the lowest point, the very bottom of the nuclear binding energy curve. Iron has the most tightly bound, stable nucleus in the entire universe.
So it's perfectly stable, it doesn't want to change.
It is too stable. Because it is at the bottom of the curve, fusing iron into heavier elements does not release energy. In fact, fusing iron is an endothermic reaction. It consumes energy.
Oh, no.
Yeah. If you force two iron nuclei together, it doesn't give you an outward push of energy. It actively sucks thermal energy out of its surrounding environment.
The ultimate betrayal. The star has been surviving for millions of years purely by generating outward energy from fusion, and suddenly, in a matter of days, the core finishes turning all its silicon into iron. The core is now a massive, dead ball of iron. Gravity crushes it. The star tries to fuse the iron to survive, and instead of getting a burst of energy out, the fusion sucks energy in. What happens to the outward pressure?
It drops to absolute zero, instantly. In stellar terms, there is no gradual fading. The star's power source completely unequivocally cuts out.
In the moment that outward pressure vanishes, gravity wins.
Gravity wins. And because we are dealing with a star of immense mass, the gravitational force is overwhelming. With the outward radiation pressure entirely gone, the delicate equilibrium is shattered. The entire weight of this massive star, millions of Earth masses of material, comes crashing down on the dead iron core in a catastrophic freefall.
How fast does this collapse happen? Let's talk real time.
In real time, the entire iron core, which is roughly the size of the Earth, collapses in under a quarter of a second.
A quarter of a second. A planetary-sized structure collapses in the blink of an eye.
The speed of the infalling material reaches a significant fraction of the speed of light, around 70,000 kilometers per second.
Unbelievable.
The core of iron is crushed so violently, so fast, that the physical limits of atomic matter completely break down. The temperature spikes to over 100 billion degrees. The density becomes so extreme that the intense pressure physically forces the electrons to smash into the protons within the iron atoms.
Electrons, which are negative, and protons, which are positive, are physically mashed together.
And when you crush a positive charge and a negative charge together under impossible pressure, they neutralize each other. They become neutrons.
Just neutral particles.
Right. In a fraction of a second, the entire core of the star, which was the size of the Earth, is compressed into a hyperdense sphere of pure neutrons roughly 20 kilometers across.
It goes from the size of Earth to the size of a small city in a quarter of a second.
And this rapid collapse halts only for one reason. Neutrons, just like electrons, physically resist being compressed beyond a certain point. It's the same quantum mechanical rule we discussed with the white dwarf, the Pauli exclusion principle, but this time applied to neutrons. It's called neutron degeneracy pressure.
The quantum elevator is full again.
The quantum elevator is full of neutrons. The collapsing core suddenly hits this unbreakable quantum wall and becomes an incredibly rigid, solid sphere of neutron matter. It simply cannot compress anymore.
But the rest of the star, all those outer onion shells of hydrogen, helium, carbon, oxygen, they are still falling inward at a massive fraction of the speed of light, right?
Exactly. The outer layers of the star don't know the core has halted. Millions of Earth masses of material are in a dead freefall inward, and suddenly, traveling at 70,000 kilometers per second, they slam into this unimaginably hard, incredibly dense, completely rigid neutron core.
It's like a car hitting a titanium wall at 1,000,000 miles an hour.
Far more violent, because it slams into the rigid core and it bounces. The inward rush of material hits the unyielding core, compresses violently, and physically rebounds. But the rebound alone isn't enough to blow the massive star apart. The real engine of the explosion comes from something nearly invisible. Neutrinos.
Neutrinos. I know of neutrinos as ghost particles. They pass through normal matter without interacting. Trillions of them are passing through my body right now from the sun, and I don't feel a thing.
Normally, yes, neutrinos are ghost particles. But during that split second when the protons and electrons were crushed together to form the neutron core, the process released an incomprehensible, staggering flood of neutrinos.
Okay.
And the collapsing matter of the star is now so incredibly dense that the neutrinos can no longer pass through it like ghosts, and they get trapped. This flood of neutrinos violently pushes against the infalling gas, transferring immense amounts of thermal energy. Combined with the physical rebound from the core, this neutrino-driven pressure drives a massive apocalyptic shockwave outward through the star.
It blows the star apart.
It completely, utterly shreds it. This is a supernova. The violent, explosive death of a massive star. The energy released in this single explosion is so immense that a single supernova can briefly outshine all the hundreds of billions of stars in its entire host galaxy combined. For a few weeks, one dying star is the brightest object in the galactic neighborhood.
That is chilling. The sheer violence of it is just awe-inspiring. And let's look at what is left behind in the aftermath of this explosion, because there are two possible remnants, depending on just how massive the original star was.
Right. For moderately massive stars, say 8 to maybe 20 or 25 times the mass of the sun, that rigid core of neutrons survives the explosion. It's left behind in the center of the expanding debris cloud as a bare neutron star.
20 kilometers across, the size of a city, but containing more mass than our entire sun.
The density is terrifying. Let's revisit our teaspoon analogy. For a white dwarf, a teaspoon weighed tons. For a neutron star, a sugar cube-sized piece of material would weigh about 1 billion tons.
1 billion tons.
Roughly the weight of Mount Everest in a sugar cube. It is the densest physical matter in the known universe. And remember the conservation of angular momentum, the figure skater pulling her arms in.
Yes, as the cloud shrank, it spun faster.
Well, imagine a star core the size of Earth spinning maybe once every few days. When that core suddenly collapses down to 20 kilometers across, it spins up to ridiculous, mind-bending speeds. Some newly formed neutron stars spin hundreds of times a second.
Spinning hundreds of times a second, beaming out intense radiation from their magnetic poles. These are pulsars, right?
Yes. If those beams of radiation happen to sweep across Earth's line of sight, our radio telescopes pick them up as perfectly regular, rapid pulses. They look like a lighthouse sweeping its beam across the cosmos, hence the name pulsar. When astrophysicist Jocelyn Bell Burnell first discovered them in 1967, the pulses were so perfectly timed they initially labeled the signal LGM1 for little green men, because they couldn't believe a natural object could tick so precisely.
And what about the most massive stars, the absolute titans of the universe? What happens when they run out of fuel and explode?
For the absolute most massive stars, those over roughly 25 or 30 solar masses, the gravitational collapse is so unimaginably powerful that even the quantum resistance of neutrons isn't enough to stop it.
It breaks the quantum elevator.
The mass of the collapsing core is so great that gravity doesn't just hit the quantum wall, it breaks the wall. The core doesn't stop compressing at 20 kilometers. It doesn't stop at 10. The laws of quantum mechanics fail. It keeps compressing infinitely until all that mass collapses into a single mathematical point of infinite density called a singularity.
A black hole.
It becomes a black hole. The gravitational pull is so intense that nothing, not even light, can achieve the escape velocity required to leave it.
The ultimate triumph of gravity. It finally wins the billions of years long tug of war. Okay, so we've covered the dramatic death of these stars, the white dwarfs, the neutron stars, the black holes. But I want to bring this all back to the very beginning of our conversation, because this raises the most important point of all, the ultimate payoff of this deep dive. Why do supernovae matter so much for us? Why are they the key to human existence?
They matter because without them, the heavy elements we rely on wouldn't exist. Remember the bottleneck. Inside a normal star, even a massive one, fusion can only build elements up to iron. Iron is the limit of the internal stellar forge.
Right. But look at the world around us. We have things vastly heavier than iron. Silver jewelry, gold rings. We use uranium in nuclear reactors. Iodine in our bodies. Where do those come from if the star's core physically cannot make them?
They come from the violent chaos of the supernova itself. While the normal, stable fusion process stocks at iron, the extreme, chaotic, high-energy conditions of the supernova explosion provide a sudden, massive injection of free energy and raw particles. For a few brief seconds during the explosion, there is an intense blizzard of free-floating neutrons flying outward. These neutrons slam into the existing atoms of iron, carbon, and oxygen so rapidly that the atoms don't have time to decay. They just keep capturing neutrons and growing heavier and heavier.
They just force feed the atom.
Exactly. This is called the R process, or rapid neutron capture. In those few seconds, elements heavier than iron are violently forged.
So the explosion itself acts as a split-second, chaotic forge for the heaviest elements in the universe.
Yes, and modern astrophysics has also confirmed that collisions between two neutron stars, which is basically a delayed, incredibly violent continuation of this stellar death cycle, also create environments extreme enough for the R process, forging massive amounts of heavy elements like gold, platinum, and uranium.
Okay, so the dying star, or colliding dead stars, managed to forge all the heavy elements. But what good does that do if they're stuck inside a dead star?
That is the beautiful, poetic utility of the supernova. It's an explosion. It doesn't just forge the heavy elements, it violently blasts them outward, accelerating them to thousands of kilometers a second, scattering them across interstellar space. It takes the carbon, the oxygen, the silicon, the iron, the gold, the silver, the uranium, and it hurls it all out into the void.
It seeds the galaxy with the manufactured materials.
Exactly. It enriches the empty gas clouds.
Yeah.
Think back to those cold, giant molecular clouds we talked about at the very beginning of the deep dive, the cosmic wombs. After a supernova sweeps through a galaxy, those clouds aren't just pure primordial hydrogen and helium anymore.
They're salted.
Right, they are peppered with carbon dust, iron flakes, oxygen gas, and trace amounts of gold. And when that newly enriched cloud eventually collapses under gravity to form a new generation of stars and a new spinning protoplanetary disk, those planets will be made of rock and metal and ice, not just gas.
This connects perfectly back to our introduction. The cliché is completely scientifically correct. You are literally made of star stuff. Every single atom in your body, heavier than helium. The carbon in your DNA, the oxygen in your lungs, the iron carrying blood to your brain right now, was forged inside the nuclear furnace of a star.
Without a doubt.
And the only way those atoms could get out of the star and into your body is if that star violently exploded and blasted its guts across space. You are made of the debris of dead stars.
It is the grandest, most profound cycle in nature. If we synthesize the whole process we just walked through, cold, tenuous clouds of simple gas collapse under gravity to become stars. Inside those stars, the fundamental tug-of-war between gravity and fusion converts light elements into heavy ones, manufacturing the periodic table.
The factory at work.
And when the fuel runs out, the stars die, some quietly leaving white dwarfs, others violently detonating as supernovae, returning their enriched, newly minted elements back into space to begin the cycle again.
That material drifts, mixes with other clouds, and forms new stars, new planets. And each successive generation of stars contains a higher concentration of heavy elements than the last.
Contextualizing humanity within this cycle is profoundly humbling. The fact that the Earth exists as a solid, rocky sphere with a molten iron core, liquid water, and an oxygen-rich atmosphere tells us definitively that our sun cannot possibly be a first-generation star. It had to be born from a molecular cloud that was already heavily enriched by the deaths of previous stars.
Astrophysics confirms this, right? Our sun is at least a second or perhaps third-generation star. It formed from the wreckage of massive blue giants that blazed brightly and died violently billions of years before our solar system even existed.
That is precisely why our sun has a rocky planet orbiting it. It's precisely why that rocky planet possessed the complex chemistry needed to brew organic molecules. And it is precisely why there is a species on that planet right now capable of looking up at the night sky, peering into a telescope, and working out this exact physical process.
It's staggering to think about. We are the universe waking up and figuring out how it made itself. We are literally dead stars, thinking about dead stars.
It's a poetic realization, but it is grounded in the absolute rigorous laws of nuclear physics, thermodynamics, and gravity.
Well, I want to leave you with a final provocative thought to mull over, building purely on what we've unpacked today. We just established that because we are made of stellar debris and our solar system is a second or third generation system, it means the exact atoms currently making up your body have already survived multiple cosmic lifespans.
Billions of years.
They were forged in a star, blown violently into space, drifted in the freezing dark for eons, gathered into a new star, blown out again, until they finally landed here to make you. If it took 3 generations of stellar life, death, and enrichment to create the chemical complexity required for human beings to exist, what unimaginable things might a 4th, 5th, or 6th generation star system be capable of building in the very distant future once the universe is enriched with even more complex stellar debris?
That is a fascinating avenue for speculation. The chemistry of the universe is not static. It is still evolving.
It really is. Keep looking up. Thanks for joining us on this deep dive.